today we will discuss our charge potential linearization. So, in the previous lecture we had discussed phi p pinch of potential in the channel, at which when the channel potential or when the surface potential is equal to the pinch of potential phi p, we had observed that we can neglect inversion charge density. So, today we will discuss how to linearize the relationship between potential and the inversion charge Qi. So, how does this help us? This linearization would help us in estimating the inversion charge density in both moderate inversion as well as in strong inversion regime. So, and there are some approximations, assumptions involved, which we will discuss as we go ahead. So, we had observed that derivative of the local threshold voltage VTB with respect to surface potential is a constant n. It is not really a constant, it is a slow varying function with surface potential. But we had observed that for a range of surface potential chi s, it is a constant and it can assume to be a constant, and we use this idea in linearizing the relationship between inversion charge and surface potential. Let us first justify it in some intuitive way. So, we know that being a capacitance, the MOS capacitor or the gate voltage to surface potential would be related in this manner, that the total silicon charge should be proportional to gate voltage minus surface potential, because we are discussing the total silicon charge here, we are not discussing inversion charge or depletion charge. The total silicon charge across any capacitance should have this relationship. So, we can also say that change in total silicon charge is related to a change in Vg minus chi s. So, there is a linear, if we keep the value of constant, see here in this we had kept Vg constant. So, for a constant Vg, this is valid, is not it? So, if we keep Vg constant, we can say that there is a linear relationship between total silicon charge and change in chi s. Okay. So, negative chi s, the negative charge in an n channel MOSFET increases as the surface potential chi s increases. So, therefore, a negative sign is coming here. Now, if we look at depletion charge, now depletion charge, as we have seen, is proportional, as we have seen in this course, is proportional to square root of chi s by ut. So, we can also say that if we are discussing change in depletion charge from a value QB naught, which is there for a certain value of surface potential chi s naught, suppose the depletion charge is QB naught, and now we are changing the surface potential by a certain value, then QB also changes by a certain value. So, now this should be proportional to. So, we have just written this in another manner, that's. So, we have said that there is an initial depletion charge which was because of an initial surface potential chi s naught, and now we are changing the value of surface potential by a delta chi s, depletion charge changes by another delta QB. So, we would say that QB is proportional to, so we use binomial theorem here, binomial approximation for small changes. So, for small changes in chi s, we can see that QB, change in depletion charge, is related linearly to change in surface potential. So, in that case, what is the change in inversion charge? Now, that is equal to change in total silicon charge minus the change in depletion charge. Now, we can see that if this is linear with chi s, this is also linearly changing with delta chi s. So, this should be as an outcome, this should linearly change. So, this should also linearly change with delta chi s. So, this in a way justifies our observation that delta chi s would linearly change with the inversion charge would linearly change with change in surface potential. We had seen in the previous lecture that the inversion charge for a given value of chi s can be given by this from the slope. So, because if the slope is, if you consider it to be a constant slope, in that case for chi p the inversion charge is 0, because that is the pinch of potential, pinch of surface potential, and Vg is constant. So, for this constant Vg, as you keep changing the value of surface potential, how does the inversion charge change? So, that you can calculate from this chi p, which is pinch of channels, pinch of potential, and also the slope, slope factor n. Now, we can write an expression using this, we can write an expression that just we are using this linear expression here. So, why is this minus sign coming here? So, this is an absolute positive value and inversion charge is negative. We are dealing with n channel MOSFET. So, its inversion charge is negative and therefore, we are showing it as a minus Q by Cox. So, when I write this expression given by this straight line as in this form, I am actually having the value of Qi inversion charge as a negative value. Chi s is smaller than chi p. So, this is a negative value, it is a negative inversion charge. I am discussing I am discussing an n channel MOSFET. So, what is the basic expression? You can also write it as Qi is equal to n Cox chi p minus chi s. So, for a given value of surface potential, chi s, you have an inversion charge this of this value, and this is a negative charge. Since and we have, so we can also write it this way. Now, this is an expression which we will use as a basic expression to get our charge potential linearization. So, what do we observe here? For very small values of surface potential, chi s naught would not be so small. So, for very small values of surface potential, you would observe that this linear relationship may not be valid. So, therefore, we can see that for very small values of surface potential, this linear change in inversion charge with respect to surface potential may not stand. Another break again. Another assumption that we had made was sheet charge approximation. So, for very small values of surface potential, the transverse electric field or vertical electric field in the channel would not be strong, and therefore, therefore it is not very safe to take charge sheet approximation to be very true. So, because of these reasons, we can see that for very small values of surface potential, this constant n is not valid, but that does not worry us much, because we are discussing for band bending from say phi p we have seen is for. So, we are discussing, take from here, we are discussing for band bending or for surface potential from phi f to 2 phi f. That is where we say that most of the important part of moderate inversion region is there, and that is where we operate circuits usually. We would not operate circuits usually for values of surface potential which is smaller than phi f. So, that is why we are not much worried about this range. We are mostly worried about the range where n is, we are discussing mostly the range where n is linear. The other point is, you would wonder, how does the surface potential change? Now, within a MOSFET itself, from the source till drain, whenever you apply drain voltage, local surface potential keeps changing along the channel from the source to the drain. So, this is therefore, change in surface potential is therefore not a very strange thing. It happens in every MOSFET whenever you apply VDS which is non-zero. Now, let us try to relate surface potential, local channel potential and inversion charge. So, for that we will use again an expression which we had derived in the previous lecture. So, we had written this expression in the previous lecture, minus square root of chi s by ut. The expression we had discussed in the previous lecture. The negative sign here appears because the inversion charge itself is negative. So, this is a term which represents in the f function that we had derived this is a term which represents inversion charge, this represents depletion charge. So, we are just looking at the total silicon charge minus depletion charge, that is how this is. We could have inverted this and written this as chi s minus 2 phi f minus v by ut plus chi s by ut minus square root of chi s by ut is equal to minus qi by gamma b c ox square root of ut. We could have written it this way. So, now if we square, and we could have further taken this term away and written it as root by ut minus qi by gamma b c ox square root of ut. Now, we could have squared both the sides to obtain exponential chi s minus 2 phi f minus v by ut is equal to qi square gamma b c square ut square minus 2. This sign you need not keep it here, right. Right. So, now what is qi sign of qi? Qi itself is negative because so now let us further simplify it. You could have written the left hand side as qi by gamma b c of taking out the common terms. You could have also written this as, you could have used the expression that we had earlier derived, that chi s is chi p pinch off potential plus qi by n c ox. This we can now use, and we can say that it is chi p minus 2 phi f minus v by ut, this natural logarithm of the earlier right hand side minus qi by n c ox. Yeah, resume. We would see when we solve this numerically, we would see that chi s by ut would usually be in normal range of operation, which we are discussing here. We would see when we solve an example problem that chi s by ut would be smaller than, would be, this would be larger than this. So, this would, and we know that qi is negative. So, therefore, for this natural logarithm to be valid, we would take this negative side, negative sign on the other side. So, that we are, since qi is negative, we are discussing, so this now is a positive quantity, and since s by ut is larger than, this term is larger than this usually, and usually in the sense where we will discuss, we will show in the example problems, this is always larger than this. So, because of that, you would find that this natural logarithm is now valid, writing it in this way. So, further we can now simplify. You now, for that we define a few terms. We define a value called q specific, and what is its value? Minus 2 n c ox ut. Now, what is its unit? Its unit you would see is that of the charge. So, it is n is voltage by voltage. So, it is unitless. C ox is farad per centimeter square, and this is voltage. Ut is voltage. So, that makes it CV, which is coulomb, farad in voltage, isn't it? Volts. So, it is coulomb. So, it has a unit of charge that you can verify. So, what is this? What is the use of this Q specific? We use it to normalize all charges, inversion charge, depletion charge, etc. And why do we want to normalize? We will see as we go ahead. Likewise, we normalize other quantities. The local potential V, we normalize with ut, and we call it small v. Likewise, surface potential chi s, we normalize with ut, and we call it small chi s. Likewise, pinch off potential chi p, we normalize with ut, and we call it small chi p. Body modulation factor gamma b, we normalized with square root of ut, and we call it small gamma b. Now, let us rewrite the previous expression in these terms. So, the left hand side was exponential chi p minus 2 f minus v by ut. So, that can be written as we had I'm sorry, there is a correction here. The left hand side was chi p minus 2 phi f minus v by ut. We can now write it as small chi p minus small 2 phi f minus small v, and what was the right hand side? The right hand side was minus qi by n c ox. We could have written it as the denominator being minus 2n c ox minus 2n c ox ut into, just a break here, resume. The right hand side can be written in this way, q by, now I divide it, earlier we had a denominator n c ox ut. Now I write it in terms of q specific. So therefore I get a numerator of 2 plus natural logarithm of qi So I had n c ox square root of ut, just correct it. We resume. We had qi by gamma b c ox square root of ut. Now this term we always are having. So what is qi minus qi by gamma b c ox square root of ut? Now this can also be written as my qi by minus n minus 2n c ox ut into square root of ut 2 into 2 divided by gamma b. So in terms of the specific charge that we had, so we are writing in terms of q specific. So what is the term in the first bracket? It is qi, it is defined as qi. Now q normalized with specific charge is qi, small qi. So inversion charge normalized with specific charge is small qi, that is the definition. So specific charge has a certain value into 2 square root of ut by gamma b. So therefore the first term can now be rewritten as 2n c ox ut into 2 square root of ut by gamma b. Now this multiplies with qi minus 2n c ox ut again into 2n. So I have corrected this n everywhere, okay, gamma b to square root of ut by, right. So this we have rewritten the earlier expression. Now we can write this in terms of our normalization, in now utilizing the normalization that we have defined. We can rewrite this as qi, 2qi, the right hand side we are rewriting as 2qi plus natural logarithm of qi into 2n by small gamma b into qi into 2n by small gamma b plus, now let us look at this chi s by ut. So we could have written chi s by ut as chi p by ut plus qi n c ox u by qi by n c ox ut. We could have written it this way. Now this can be written as small chi s is equal to small u p, that is normalized chi p plus 2 qi, 2 times normalized qi in terms of specific charge. So therefore this term now becomes 2n by small gamma b into square root of small chi p plus 2 qi. I am sorry, there is a correction, I will do it again. Yeah. So this can be written as small chi s is small chi p minus 2 times normalized qi. That is because qi is negative and q specific is also a negative value. So therefore you get a minus q 2 qi term here. So now therefore by when we rewrite chi s by ut, here you obtain chi p minus 2 qi. So now what is this? So this is the left hand side. So how can we write the right hand side? The right hand side is we rewrite it in this manner. So we are just dividing by the specific charge, so that we normalize, and therefore we keep these factors in the numerator. So, natural logarithm of qi by n gammas into square root n c gamma cox square root of ut. So, that gamma cox square root of ut we are rewriting in this way. So, that we have the specific charge in the denominator, and minus sign moves from the numerator to denominator. So, that is what we do here, and within these braces again we do the same for qi. So, that is how we are rewriting the previous expression. So, what is this? This is 2 qi, 2 times normalized specific charge plus natural logarithm of again normalized specific charge into this plus now we have the term square root of chi s by ut. How do we rewrite it? Square root of chi s by ut can be written as square root of chi p by ut plus qi by n cox ut. So, now what is this? This is normalized surface potential, normalized pinch of potential minus again 2 times qi. So, we replace this with this here within the braces. So, what is our final expression? Small chi p minus 2 phi f minus small v is equal to 2 qi plus natural logarithm of qi plus natural logarithm of 2 n by gamma b into 2 n by gamma b qi plus 2 times square root of chi p minus 2 qi. We call this term as small vsh. So, we can rewrite this as small chi p minus 2 phi f minus small v is equal to 2 qi plus natural logarithm of qi plus small vsh. We can further rewrite this as, we can take this small vsh term on the left hand side and rewrite it as this. We can also simplify this vsh as being natural logarithm of 4 n by gamma b square root of small chi p. Now, what is this? This we have been able to obtain because p pinch of potential is much larger than inversion charge, normalized inversion charge qi. That we can justify using some numerical examples that we will solve, but we can also intuitively see that the inversion charge we are discussing is below the is in moderate, if it is moderate inversion. So, in that case, or for any gate voltage, this pinch of potential chi p is a large value. Pinch of surface potential chi p is a large value, and its normalized value, it is normalized with thermal voltage. At 300 Kelvin, it is 26 millivolts. Now, inversion charge when normalized is a relatively small value, and it is normalized with a relatively larger specific charge. So, in magnitude. So, therefore, you would observe that always this is in the range of our operation of our interest. This is equal to this, you can neglect with square root of chi p itself. So, then and q again this term can be neglected with respect to square root of chi p, and therefore, this results, this is approximately equal to this simpler term. So, this is our final expression which we would be using. So, what we observe is that this VSH is a technology and device related parameter. It does not change with gate voltage. QI changes, small changes with gate voltage, but that is relatively a small value, and therefore, this VSH does not essentially change with gate voltage. So, this we use in linearization. So, what is this small v? Small v that we see here is local surface potential. As we move from the source towards the drain, it is the local surface potential which changes from a 0 value to a value VDS divided by UT. Now, normalized local surface potential. So, now we define, we will further now discuss the value of inversion charge with respect to the local surface potential, because it is this local surface potential which changes from source to drain, and when we change the value of drain to source voltage, it is the local surface potential that changes. So, therefore, we would now want to obtain this inversion charge in terms of local surface potential. That is the exercise that we would do in the next lecture. In this lecture, we had discussed linearization of inversion charge and surface potential, and we assumed that the slope factor n is a constant in the range of our interest, and we obtained an expression relating inversion charge, though it is an implicit expression, but an expression relating inversion charge with respect to the surface potential, that is local surface potential, local surface voltage V, and pinch off surface potential chi p. Now, this pinch off surface potential is a function of gate voltage. So, therefore, all this using these expressions, one can relate inversion charge with respect to gate voltage and local and gate drain voltage. Local surface potential is local surface voltage small v is a function of drain voltage, and local surface and pinch off voltage chi p is a function of gate voltage, and therefore, we can now relate inversion charge with respect to gate voltage and drain voltage. That is the matter of further discussion in the coming lectures. Thank you.